Hi everyone, my name is Ashley Bedford and welcome to day 5 of the hashtag 30 Days of Code Challenge with Educative. I am super excited for this problem. We are going to be solving loud and rich. So let's get into it. Today's problem is loud and rich, and it's a fantastic example of how real relationships between data points can form a graph, even when the problem doesn't explicitly say the word graph. So let's turn relationships into visuals and break down how to think through this one step by step. The problem starts by describing a group of n people labeled from 0 to n minus 1. Each person has two properties, their amount of money and their quietness level. Then it says, richer of I equals A comma B, means that person A has more money than person B. So person A to person B means A is richer than B. And the quiet array tells us how quiet each person is, where smaller numbers mean quieter people. Finally, the goal is to return an array answer of x equals y, where y is the quietest person among everyone who is at least as rich as x. So if you think about it, we're not comparing money values directly. We're comparing relationships between people. Let's break the problem statement piece by piece. When it says there are n people labeled 0 to n minus 1, that means each person is a node in our graph. Richer of I equals A comma B means there's a directional edge from A to B. A is richer than B. Quiet of I gives a value on each node, like a label or weight. And no contradictions means there are no cycles. Nobody can be richer than anyone who eventually points back to them. So this forms a DAG, a directed acyclic graph. Once you realize that, everything changes. Because now it's not about iterating through lists. It's about traversing relationships in a graph. This is the aha moment. The reason this is a graph problem is because richer than is a directional dependency. You can't just sort or filter these numbers. They're connected through relationships. And since it's acyclic, meaning there's no circular richer chain, we can safely use either DFS, depth first search, if we're collecting information upward, or topological sorting /BFS if we're pushing information downward. That's the mental unlock. We're no longer comparing raw values. We're navigating dependencies. Once you recognize it's a graph, there are two natural directions you can think in. Option 1, rich to poor. This means the arrows go from richer to poorer. You'd use a BFS or topological order starting with people who have no one richer. That's good when you're pushing information downward. Option 2, poor to rich. This means the arrows go from poorer to richer. You'd use DFS with memoization. Each person asks all richer people for their quietest ancestor. That's best when you're collecting information upward. In this problem, the poor to rich approach is cleaner because each person only needs to ask upward and remember the quietest rich person they can reach. Let's build the actual graph. Here's an example. Richer equals from left to right. Sublist 1, 0, comma, sublist 2, 1, comma, sublist 3, 1. Quiet equals from left to right, 3, 2, 5, 4. If we read this in poor to rich direction, person 0 connects to 1. Person 2 connects to 2 and 3. Person 2 and 3 have no richer connections. That means 1 is richer than 0. 2 and 3 are richer than 1, and 2 and 3 are the top of the chain. Now we can clearly visualize the relationships we'll traverse. Here's the simplest way to think about it. For each person, 1, look at everyone richer than them. 2, compare quietness. 3, pick the smallest quietness value. That's a fine start, but there's one big problem. We'll end up repeating the same searches over and over. If multiple people share richer ancestors, you'll recompute the same paths. That gives you O of n squared time. Too slow for larger graphs. Let's look at what the naive version looks like in code. We loop through each person, recursively explore who's richer than them, and track the quietest among all paths. It works logically, but it's inefficient. We call DFS for the same people multiple times because we're not storing results. In small examples, it'll run fine, but in big graphs, this rework becomes very costly. The naive version has time complexity of O of n squared because each node can re-trigger full DFS chains. The space complexity? O of n plus e, where e is the number of edges in the graph. This isn't terrible for small inputs, but if there are thousands of people and relationships, this becomes exponentially slower. So how do we fix that? With memoization. We remember what we already solved. The idea is each person asks their richer neighbors who their quietest ancestor is. Once that's computed once, we save it in ands of x, so it's never recomputed. This makes the algorithm run in O of n plus e time because every node and edge is visited just once. Here's how the traversal happens conceptually. Number 1, start at person 0. They ask, who's richer? That's person 1. So step number 2, person 1 asks, who's richer? That's people 2 and 3. Then step 3, people 2 and 3 have no richer connections, so they're base cases. And step 4, backtrack and compare quietness values. At the end, each person's answer points to the quietest person reachable through the richer chain. So the resulting array visually is from left to right, 1, 1, 2, 3. In the optimized code, we add one simple but powerful check. If ands of person not equal to -1, return ands of person. That single line ensures that if we've already computed the quietest person for a node, we never rerun DFS for it again. By combining recursion with caching, we eliminate all redundant work. With memoization, time complexity is O of n plus e. Each node and edge is only explored once. The space complexity, O of n plus e as well. We store the graph and the recursion stack. This is a massive improvement from O of n squared. The key is that memoization makes every node's answer final after its first visit. So how do you recognize a graph problem like this in the wild? Here's the pattern to look for. You see relationships, not just numbers. There's directional dependency, like more than, depends on, or comes before. The data doesn't form a simple line, it forms connections. What you learned here, recognize relational patterns and represent them as edges. Use DFS or topological logic to navigate those connections. And most importantly, memoization prevents redundant work. And that's a wrap for day 5. Thank you so much for joining us. If you like this video, like it, share it, subscribe. We are going to be doing one LeetCode problem every day this month as a part of the hashtag 30 Days of Code Challenge with Educative. So we are going to see you for the next day.